A modulator circuit consists of a multiplier, which is the main component, which multiplies two signals, modulated signal MT and carrier signal cos omega ct. After multiplication, we are getting a modulated signal, that is MT cos omega ct. So here we are getting S1t, that is modulated signal, will be equal to MT cos 2 pi fct. So the signal frequency content is centered at plus minus Fc. So here S1f will be equal to 1 by 2 m f minus Fc plus 1 by 2 m f plus Fc. This allows changes in the amplitude of the sinusoid S1t to be proportional to the message signal. Now let us consider a sinusoid signal. So St is equal to At cos omega ct plus phi t. So here three parameters are there: At, omega ct and phi t. So the three parameters, At is the amplitude, omega ct is a frequency and phi is a phase. So the message can be used to modulate any of the three parameters to allow ST to carry the information from transmitter to receiver. So out of these three parameters, a modulator use or vary any of the three parameters one at a time to transmit the information signal from transmitter to receiver. That means variation in amplitude or variation in frequency or variation in phase carries the message signal from transmitter to receiver. Amplitude At is proportional to the MT, so that is called as amplitude modulation. If frequency is proportional to MT, then it is called as a frequency modulation, and if the phase is proportional to message signal MT, then it is called as a phase modulation. Now the double sideband amplitude modulation. Here amplitude modulation is characterized by an information varying carrier amplitude At, that is a linear function of the baseband, that is message signal MT. So at the same time, when only amplitude is varying, the other parameters such as angular frequency omega c and the phase will remain constant. So here we are assuming phase is equal to 0. If the carrier amplitude is made directly proportional to the modulating signal MT, then the modulated signal is MT cos omega ct will shift the spectrum of MT to the carrier frequency. That means in amplitude modulation, after modulation, it shifts the spectrum of message signal to the carrier frequency Fc. So if MT is equal to MF, then MT cos 2 pi FCT will be equal to 1 by 2 M F plus Fc plus 1 by 2 M F minus Fc. So MF minus Fc is MF shifted to what direction? So it will be shifted to the left of Fc, whereas MF plus Fc, that is MF is shifted to the right direction, that is to USB. If the bandwidth of MT is B, then the bandwidth of modulated signal will be equal to twice B. So why twice B? How twice B? So as we know that the bandwidth formula is the range of frequency, or it is the difference between the upper and the lower frequency. So if our upper frequency is FUSB and lower frequency is FLSB, so the difference is FUSB minus FLSB will give you a bandwidth of modulated signal. So that bandwidth comes around to be twice B. The modulated signal spectrum centered at plus minus Fc or omega c radian per second. It will consist of two parts, upper sideband part and the lower sideband. A portion which lies outside plus minus Fc, that is called as a upper sideband, and the portion which lies inside plus minus Fc is called as a lower sideband. So the modulated signal in double sideband suppressed carrier will not have a discrete carrier component, or you can say a discrete component of the carrier frequency Fc will not be there. So that is carrier is suppressed, and as a result we are getting a double sideband suppressed carrier, that is DSBSC. So here this is a modulator circuit where the main component is multiplier, which multiplies the modulating signal and a carrier signal. So after multiplying we are getting a modulated signal, that is MT cos omega CT. The envelope of AM, it is like this. This is plus MT, this is minus MT, this is the envelope. This envelope is nothing but the multiplication of message signal with the carrier signal. At zero crossing, we are getting a phase reversal. Second is the bandwidth. This is the how we can calculate the, from this how we can, we'll see how we can justify the bandwidth of modulated signal. So this is the upper sideband and this is the lower sideband. So upper sideband it is at plus B and the lower sideband it is at minus B. So as we have seen that the bandwidth is a range of frequency, or it is the difference between two frequency, upper frequency and the lower frequency. So this is the upper frequency and this is the lower frequency. So the bandwidth B will be equal to upper minus lower, that means plus B minus of minus B. So it will be B plus B. So it will be twice B. So as we have seen in the earlier slide that bandwidth of modulated signal will be equal to twice B. And the second part is the portion which lies outside the plus Fc. This is a portion which lies outside the plus Fc and minus Fc, that is called as the USB. And the portion which lies inside the plus Fc and inside the minus Fc. So this is the inside portion of plus Fc and minus Fc, that is called as a LSB. Outside portion it is USB and the inside portion of plus Fc and minus Fc is LSB. Now let's see the relation between bandwidth and the carrier frequency. So relationship of B and to Fc. So from figure C, if Fc is greater than or equal to bandwidth, it avoids overlapping of modulated spectra which is centered at plus minus Fc, and if Fc is less than bandwidth, then the overlapping will be there. The two message signal will get overlap with each other and MT it's get distorted during modulation. So this will be make it difficult to recover MT from MT cos omega CT. So the practical factor may impose additional restriction on Fc. Example, in broadcast application, a transmit antenna can radiate only a narrow band without distortion. Now here's the reflection question. What is DSB-FC and why DSB-SC? So what is DSB FC? So the transmission of signal which contains a carrier along with two sideband is called as a double sideband full carrier, and a system with this is called as a double sideband full carrier system, or simply you can call it as a double sideband full carrier DSB-FC. The plot it is like this. It consists of a full carrier and two sideband, upper sideband and the lower sideband. The upper sideband frequency is Fc plus Fn and the lower sideband frequency is Fc minus Fm, and the carrier is Fc. So here we are transmitting a signal along with the carrier signal and two sidebands. So that's why it is called as a double sideband full carrier. And the bandwidth of this signal will be equal to upper sideband minus lower sideband. So it will be Fc plus Fm minus Fc minus Fm. So after simplifying, it comes around to be twice Fm. So for double sideband full carrier, the bandwidth will be equal to twice the modulating frequency. Then why DSB-SC? DSB-FC transmission is insufficient because two-thirds of the power is being wasted in the carrier which carries no information. So if this carrier is suppressed, so it will save the power, and the saved power is distributed to the two sidebands. Then such a process is called as a double sideband suppressed carrier, and such a system is called as a double sideband suppressed carrier system, or simply you can call it as a double sideband suppressed carrier or DSB-SC. The plot is shown. So in this case, what we are doing, we are suppressing the carrier. So carrier is suppressed and only two sideband, upper and lower sideband, are transmitted. So such a signal where the carrier is suppressed and only two sideband are transmitted is called as a double sideband suppressed carrier. So the bandwidth for this will be equal to upper sideband frequency minus lower sideband frequency. So it will be equal to Fc plus Fm minus Fc minus Fm. So after simplifying, it comes to be around twice Fm, which is similar to the spectrum of double sideband full carrier. So bandwidth requirement for both the signal DSB-FC and DSB-SC will be same, but the power in double sideband suppressed carrier we can saved by suppressing the carrier. So here an example. So sinusoidal carrier has amplitude of 20 volt and a frequency for the carrier is 30 kilohertz. If it is amplitude modulated by a sinusoidal voltage of 3 volt and a frequency of 2 kilohertz, calculate upper sideband frequency and lower sideband frequency. So here two signals are given. One is the carrier signal whose amplitude is 20 and frequency, that is Fc, is equal to 30 kilohertz, and the modulated signal voltage is 3 volt and frequency is 2 kilohertz. So as per the formula, FUSB will be equal to Fc plus Fm. So it will be around Fc is 30, Fm is 2. So 30 plus 2 is 32 kilohertz. Whereas FLSB will be equal to Fc minus Fm. So that is 30 kilohertz minus 2 kilohertz, which comes around to be 28 kilohertz. So this is how, by using the formulas for FUSB and FLSB, we can calculate the frequency of this. And if we take the difference between these two, FUSB and FLSB, we can calculate the bandwidth of modulated signal. So FUSB minus FLSB, that is 32 minus 28, will be equal to 4 kilohertz. So that 4 kilohertz will be the bandwidth of modulated signal. So this is how we can solve numericals on amplitude modulation.